Welcome back. Today, we're diving into a classic problem in combinatorics that brings together several powerful ideas. Our objective is to count the number of distinct ways to color a cube. We'll assume we have 3 distinct colors, say red, green, and blue, and we can use any of them for each of the cube's 6 faces. So, we have 3 colors and 6 faces on the cube. A key point is the word distinct. We're not just counting face-by-face assignments, we need to account for rotational symmetry. If we can rotate a colored cube to match another, they are considered the same coloring. Let's first consider the naive approach. If we ignore symmetry for a moment, how many ways are there to color the cube? There are 6 faces on the cube. For each face, we have 3 color choices. By the multiplication principle, we multiply the number of choices for each face. 3 times 3, 6 times. This gives us a total of 3 to the power of 6, which is 729. So, there are 729 face-by-face colorings possible. However, this number overcounts the distinct colorings because it doesn't account for rotations. For example, if we color one face red and the rest green, rotating the cube might make a different green face appear at the top, but it's still the same coloring. To deal with this symmetry, we'll use a powerful tool, Burnside's lemma. Let's state Burnside's lemma. Let X be a set of objects, and G be a finite group that acts on X. The number of orbits under the action is given by 1 over the size of the group G times the sum over all group elements G in G of the number of fixed points for that element. In our problem, the set X is the set of all possible 3 colorings of the cube's 6 faces. That's our 729 colorings. So, our set X is the set of 3 to the 6th, or 729 colorings. The group G is the rotational symmetry group of the cube. We need to figure out its size, which is the number of distinct rotational symmetries. We'll call this group G. For each element G in this group, that is, each rotation, we need to find the number of colorings, X times G, that are left unchanged by that specific rotation. Before we apply the lemma, let's determine the size of our group G, the rotational symmetry group of the cube. We can think about this by imagining placing a cube down on a table. The bottom face can be any one of the 6 faces. Once that face is fixed, say it's red, we can rotate the cube around the vertical axis of that face. Since a square face has 4 sides, there are 4 rotations possible around that axis. Multiplying 6 by 4, we find the total order of the group is 24. So, the size of our group vertical bar, G vertical bar, is 24. Now, let's categorize the 24 rotation elements. We can do this by their axes of rotation. Remember, for each G in G, we must find X first G, the number of colorings fixed by that rotation. Our first category is the most obvious one, the identity rotation. The identity, denoted A, doesn't change anything at all. It fixes every single coloring in our set X. Case 1. Identity rotation, E rotation, 0 degrees around any axis. Therefore, the number of colorings fixed by the identity is simply the total number of colorings, which is 3 to the 6th, or 729. Our next category involves rotating around an axis that passes through the centers of 2 opposite faces. There are 3 such pairs of faces, giving us 3 axes of this type. For each of these axes, we can perform a 90-degree rotation. This swaps the 4 faces around the axis. For a coloring to be fixed by this rotation, all 4 of these side faces must have the same color. The top and bottom faces can be any color. This creates 3 orbits of faces. If we're using 3 colors, the number of colorings fixed by a 90-degree rotation is 3 times 3 times 3, or 27. There are 6 such 90-degree rotations, 2 for each of the 3 axes. They are 90 degrees clockwise and 90 degrees counterclockwise. We have 6 rotations of 90 degrees. What about a 180-degree rotation around one of these axes? This swaps 2 pairs of side faces. For a coloring to be fixed, these 2 swapped pairs must have the same color. This gives us 4 orbits of faces. With 3 colors, there are 3 to the 4th, or 81, such fixed colorings. There are 3 such 180-degree rotations, 1 for each axis. Our third category of rotations are those that pass through the midpoints of opposite edges. There are 12 edges on a cube forming 6 opposite pairs, so there are 6 such axes of rotation. A 180-degree rotation around one of these axes swaps 2 pairs of faces. The 2 faces that are part of the edge on the axis must have the same color, and the 2 faces on the opposite edge must also have the same color. The 2 faces not involved in these edges must also have the same color. This creates 3 orbits of faces. For a coloring to be fixed, faces in the same orbit must be the same color. With 3 colors, this gives us 3 to the 3rd power, or 27 fixed colorings. There are 6 such rotations, 1 for each axis. Finally, we have rotations around axes that connect opposite vertices. There are 8 vertices on a cube, forming 4 opposite pairs. Thus, there are 4 such axes. For each axis, we can perform a 120-degree rotation. This rotation moves the 6 faces in 2 groups of 3. The 3 faces that meet at the top vertex form one cycle, and the 3 faces that meet at the bottom vertex form another cycle. For a coloring to be fixed, all faces in the first orbit must be the same color, and all faces in the second orbit must be the same color. With 3 colors, there are 3 times 3, or 9, fixed colorings. Since there are 4 axes and each has 2 120-degree rotations, there are a total of 8 such rotations. Let's check our total number of rotations. We have 1 identity, 6 of 90 degrees, 3 of 180 degrees through faces, 6 of 180 degrees through edges, and 8 of 120 degrees through vertices. That's 1 plus 6 plus 3 plus 6 plus 8, which equals 24. This matches our calculated size of the group G. Now we can put it all together using Burnside's lemma. We substitute our values into the formula. The number of distinct colorings is 1 over 24, times the sum of all our fixed points. We can see that we have some terms repeating. We have 6 times 3 cubed, twice. Let's simplify the sum. 3 to the 6th is 729. 6 times 3 cubed is 6 times 27, which is 162. 3 times 3 to the 4th is 3 times 81, which is 243. And 8 times 3 squared is 8 times 9, which is 72. Adding these up gives us 1368. So the total sum is 1368. We divide this by 24. The result is 57. This is our final answer. There are 57 distinct ways to color a cube using 3 colors, considering rotational symmetry. Just to recap our process, we used Burnside's lemma to account for the rotational symmetry of the cube. We identified the group of rotations and determined its size was 24. We then systematically calculated the number of colorings fixed by each type of rotation. 1 identity, 6 rotations through opposite faces of 90 degrees, 3 of 180 degrees through opposite faces, 6 of 180 degrees through opposite edges, and 8 of 120 degrees through opposite vertices. Finally, we applied Burnside's lemma, summing the fixed points and dividing by the order of the group to arrive at 57. This method is a powerful and systematic way to count distinct objects under group actions, and it's a fundamental concept in combinatorial mathematics. Thank you for watching.